Hello, this is Professor Roman. Let's continue the ring theory lectures. Ready now to start Chapter 6, Polynomials. And I don't need to tell you, I'm sure, that polynomials play a very significant role in the study of mathematics. In this chapter, we are going to take a look at the basic properties of polynomials over fields and also over more general rings. A few facts before we start. I'm going to generally reserve the symbols R, S, and T for rings and F, G, and H for fields. So if you see this symbol F square bracket X without further explanation, you can assume that F is a field. I'm trying not to do that. I'll try to mention it each time, but just in case I forget, now you know about this. If R and S are rings and R is contained in S, and if F, script F here, is a family of polynomials over the smaller ring R, non-empty family, then the root set of the family in S is the set of all roots in S of the polynomials in the family. When we want to include duplicate roots, roots of multiplicity greater than 1, then I'm going to use the term root multiset. Another definition, let R be a ring. A polynomial, P of X over R, just for terminology, this could be read in two ways. A polynomial in R square bracket X, or a polynomial over R. Okay. Splits over a ring S containing R if P of X can be written as a product of linear polynomials over S. So that product would look like this: a constant in S times some linear factors where the coefficients are in S. And this set then, R1 through Rn, is the root multiset of P of X in S. Now, it's useful to be able to compare the behavior of a polynomial, P of X, over a field F with its behavior when we think of P of X as having coefficients in a larger field, E. So there's an obvious example. A nonlinear real polynomial that's irreducible over R is no longer irreducible over C. In fact, it splits over C. So this is the kind of thing we want to explore in a more general setting. So we need this formal definition. A subfield of a field E is a non-empty subset, F of E, that's a field in its own right using the restricted operations of E. This is the same definition, same form that we use for vector spaces and subspaces, for groups and subgroups, rings and subrings. But there's a little bit different terminology in field theory. When this happens, we say that E is an extension of F and write this. Now, this is a strictly less than sign. Some people would write a less than or equal to sign. Somewhere I picked up the habit of a less than sign, and I don't think I'm alone in that. But this is not meant to imply that E and F couldn't be the same. They could be equal. And just for convenience, I'm going to refer to this whole notation as a field extension. It's actually somewhat more appropriately called a tower of fields, but we'll get into that when we do the next lecture series on field theory. So if E is an extension of F, and if S is a subset of E, then the subfield of E generated by S over F, this is the terminology, denoted this way, is the intersection of all subfields of E that contain both F, the subfield, and S, the subset. And one has to verify, it's not difficult, that the intersection of these subfields is a subfield. It will be the smallest subfield containing F and S. And this sort of thing we've seen before as well. We will have much to do with the field of fractions of an integral domain. So if you're a little fuzzy on that, this will be a good time to review that concept. And for readability's sake, I'm going to change the notation. We've been denoting this by fract R, and I'm not the only one who does that. But I'm going to use F sub R for the field of fractions of the integral domain R. It'll just make things a little more readable, I think. Now, there's a lot to cover in this chapter concerning polynomials, and rather than just plunge in, I thought it would be a good idea to outline what it is that we're going to do, so you'll have a good sense of what's coming. First, we will say that a factorization of a polynomial f of x into a product of polynomials is over a ring S if g of x and h of x are polynomials in S. In other words, their coefficients belong to S. Factorization over a ring. Now, the first thing we're going to examine is inheritance. This is a very important question. If a ring R has a certain property, such as being an integral domain or a principal ideal domain, is that property inherited by the polynomial ring R square bracket x? As we will see, the weaker properties of being an integral domain or a unique factorization domain are inherited. But the stronger properties of being a principal ideal domain or Euclidean domain are not inherited. They may happen accidentally, but they're not inherited. Next, irreducibility. If R is a unique factorization domain with the field of fractions f sub R, what is the relationship between the irreducibility of a polynomial over R and that same polynomial thought of as being over f sub R? We will see that the relationship is actually pretty straightforward, fortunately, but it does have one wrinkle, because there are non-trivial factorizations over R. Non-trivial, if you recall, means that the two factors are non-zero non-units that become trivial when viewed as factorizations over f sub R. And this is due to a simple fact, assuming R is not a field, in which case R would be FR. Non-zero, non-unit constants in R become units when viewed as elements of f sub R, the field. Every non-zero element's a unit in a field. So some non-trivial factors when viewed over R become trivial factors when viewed over f sub R. And to illustrate, I know this could be confusing, coming pretty fast. consider this polynomial over the integers factors 2 times 2x squared plus 1. This is typical of what happens. This is a non-trivial factorization over the integers because both of these factors are non-zero non-units. 2 is not a unit, has no inverse in the integers. But over the rationals, 2 does have an inverse. It is a unit, and so this factorization is trivial. And so f of x is reducible over the ring Z, but irreducible over the larger field Q. And that is somewhat counterintuitive. You might think that moving to a larger base, in this case field, would permit more factorizations and thereby reduce the number of irreducible polynomials, more likely to be factorable over the bigger base field. That's actually true, except it's only true in terms of factorization into factors of strictly smaller degree. In other words, non-units. Okay. Something else is going on here because of the situation with constants starting out as non-units in the ring and becoming units in the field. So that's the exception, that's the wrinkle. And we'll go over all this in detail at the appropriate time. Division algorithm. If R is an arbitrary ring, does the polynomial ring R square bracket x have a division algorithm? And if not, is there anything we can say? Well, it turns out that there is a restricted division algorithm. And here's a simple example. Suppose that f of x is a polynomial over R. We can always use x as the divisor and write f of x equals q of x times x plus r, where little r is in the ring. This we can always do. On the other hand, in this polynomial ring Z4 square bracket x, we cannot write this. We can't use 2x as a divisor, because if this equation were to hold, x divides this term and this term, therefore it divides r, which means r has to be 0, resulting in this, which cannot happen for any polynomial over Z4. Okay? And I'll let you ponder that. Polynomials as functions. One gets used to thinking of polynomials probably more as functions than as formal expressions, because in calculus we think of them as functions pretty regularly. But the question remains, how do polynomials over a ring behave as functions on the ring? For example, a real polynomial is the zero function, sends everything to 0, if and only if f of x is the 0 polynomial. And this is true in more generality for polynomials over any infinite field. But consider this. This polynomial, x squared minus x, over the finite field Z2 is a non-zero polynomial, but it's the 0 function. Because if you put in x equals 0, you get 0. If you put in x equals 1, you get 0. Okay? So if the base is not an infinite field, then you can have a non-zero polynomial being the zero function. Greatest common divisors. Suppose that we have a field extension and a couple of polynomials over the smaller field. Since f and k are fields, these two polynomials have greatest common divisors over both the smaller field and the larger field. What's surprising is that the greatest common divisors are the same. Another way to say it is the greatest common divisors are field independent or belong to the smallest field containing the coefficients of the polynomials. And we'll get into all that in careful detail. But what it means is that if two polynomials have a non-trivial common factor over the larger field, then they must have a non-trivial common factor over the smaller field as well. So for example, if two real polynomials have a non-trivial common factor when thought of as complex polynomials, they also have a non-trivial common factor when thought of as real polynomials. Roots. What can we say about the roots of a polynomial over a ring? Well, we will see that the familiar fact that an element in this case the ring, is a root of a polynomial. It's called the element a, if and only if x minus a is a factor. This still holds for polynomials over any ring. Another familiar fact is that a polynomial of degree n has at most n roots. This will hold over any integral domain. But, for example, z8, which is not an integral domain, over z8, these four elements, 1, 3, 5, 7, are roots of this quadratic polynomial. Four distinct roots, degree 2. Splitting fields. We will see that if f of x is a non-constant polynomial over a field f, there is always an extension of f with the property that the polynomial splits over that extension. Very famous result. In fact, any polynomial has what is called a splitting field over f, and that's the smallest extension for which the polynomial splits. In fact, the same is true for any non-empty family of polynomials over f. There's the smallest extension in which all the polynomials of the family split. Also, there's the smallest extension, S, of the field f, over which every non-constant polynomial over f splits over S. And this is called an algebraic closure of f. And you may already be familiar with the fact that the complex field is an algebraic closure of the real field. We'll touch upon this somewhat briefly in this chapter and do a much more careful look at this concept and field extensions in general in the next lecture series on field theory and Galois theory. There are several types of field extensions that are very important in field theory. Finite extensions, algebraic extensions, transcendental extensions, normal extensions, separable extensions, Galois extensions. Multiple roots. we will take a look at the issue of multiple roots in polynomials, and we're going to see that the presence of multiple roots for a polynomial is actually related to the behavior of the formal derivative of that polynomial. No limits, we don't need them. Just derivative of x to the n is nx to the n minus 1. Also, it is possible for an irreducible polynomial to have multiple roots. This might seem a little strange too. It doesn't happen very often. That is to say, it doesn't happen over fields of characteristic 0, rationals, reals, complex, or over finite fields. But it can happen over more unusual fields, which we will have to discuss at the appropriate time. Finally, we're going to take a look at a very famous criterion for showing that a polynomial over an integral domain is what we will call degree-wise irreducible. In other words, it cannot be factored into two polynomials of smaller degree. This is called Eisenstein's criterion. So there you have the game plan for this chapter, and we are ready to begin our journey.